when you use the equation Q equals mc delta T in the laboratory setting, what you'll use is something called a calorimeter. And a calorimeter is really just a fancy term for something that doesn't allow much heat to escape. A lot of times a calorimeter is really something as easy as just 2 coffee cups put together. And then you put like a piece of cardboard on top of it, and that's what a calorimeter is a lot of times. So you don't lose a lot of heat. So when the heat gets transferred from one thing to something else, you don't lose a lot of heat going out of the styrofoam cups. You don't lose a lot of heat going to the air. And you usually can get some pretty good results using just a couple of coffee cups put together, styrofoam cups put together with a piece of cardboard on the top. So you put some water into the coffee cups, you put 2 things together, you put the lid on it, you put a thermometer in there, and you check to see how much the temperature has gone up by. So if the temperature of the water, remember there's the system and there's the reaction itself, and then there's the surroundings. So the system, remember, is the reaction. The surroundings is everything around it. So the water, for example, would be the surroundings. If the surroundings, the water temperature goes up, again, that is an exothermic process. And that is releasing energy to the surroundings. The surroundings are increasing in energy, and so their temperature is going up. If the temperature goes down, then it is an endothermic process. Okay, so let's look at again, like many things, this is just easier just looking at some examples. So these are some possible questions that you could see dealing with Q equals mc delta T, a lab situation, etc. So propane is the gas that's commonly used in gas grills. A sample of propane with a mass of 44 grams is completely burned in oxygen, and in the process it releases 2,002 kilojoules of energy. This chemical reaction is brought into contact with a water bath, and the transfer of energy from the reaction to the water takes place. Water has a specific heat of 4.18, and we're going to assume, which doesn't really happen, that 100% of the energy generated by the propane is transferred directly to the water, causing the water temperature to increase. So part A, in which direction does the energy flow? It's going to flow from the propane to the water. Okay, and how do we know that? Because the temperature of the water is going to increase. So the water is absorbing the heat. The propane is giving off of the heat. You could think of the water as it being an endothermic process. It's absorbing heat, whereas the propane process, which is part C, is the combustion of propane, an exothermic or endothermic process. That is an exothermic process. And explain your answer, because it gives off heat. Okay, it releases heat to the surroundings. In this case, the water is the surroundings. Okay, part B says, calculate the change in temperature in 20 kilojoules of water, or kilogram, not kilojoules, kilograms of water. So first of all, we have our Q equals mc delta T. So here's where we got to be a little bit careful. Okay, because our 4.18, our specific heat, is in joules over grams Kelvin. So that means we either need to move the kilojoules to joules or vice versa. So I'm going to move kilojoules 2002 to convert from kilojoules to joules. You multiply by 1,000. So I'm just going to put 3 more zeros on the end. So again, we're using Q equals mc delta T here. So the mass is 20 kilograms, and again, it's grams here. So kilograms to grams, again, is also multiplied by 1,000. And then the specific heat is 4.18 joules over grams Kelvin. And then the temperature change is what they're asking you for. So now we just go to our calculator. I'm going to take 2,002,000, divide by 20,000, divide by 4.18. And that's going to give me a temperature change roughly of 24, again, either Kelvin or Celsius. So the temperature of the water is going to go up by 24 degrees using that Q equals mc delta T equation. Okay, example 2. A student investigates a pure metal X The student takes a 100-gram piece of the metal and heats it to 500. So it goes up by 400 degrees, okay? Then places it on a 1,000-gram block of ice at 0 degrees. The ice partially melts and the final temperature of the metal, ice, and the melted water is 0. The student calculates the experimental value of the specific heat capacity of the metal X and records it as 0.90. Calculate the magnitude of the energy change of metal X during the experiment, okay? So in this case, we've got the specific heat is 0.90 grams per degrees Celsius. So the magnitude of the energy change, that's going to be our Q value, that's our energy. The mass of the piece of metal is 100 grams. The specific heat is 0.90 joules over grams degrees Celsius. Okay, it's at 500 degrees, and then it goes all the way down to 0. Okay, so what's that a temperature change of? It's a change of 500 degrees Celsius. Okay, so the magnitude of the energy change is going to be 100 times 0.9 times 500. It's going to be a fairly large number, 45,000 joules. If you wanted to put it into kilojoules, it'd be 45 kilojoules. Either of those answers would be accepted. Okay, and then part B says calculate the mass of ice that melted by metal X if 330 joules of heat are needed to melt 1 gram of ice. So again, think about the equation Q equals mc delta T. That's our Q value, so 330 joules, okay, is equal to the mass. Hold on here, let me think here for just a second. Let's walk through this here real quickly. So if 330 joules of heat are needed to melt 1 gram of ice, and they want to know how much ice was melted, well, how much heat was given off by the metal? 45,000 joules. So 45,000 divided by 330, 45,000 divided by 330 equals 136 grams of ice. And let's check and make sure, does that make sense? Well, we had 1,000 grams. So could we have melted 136 of those grams? Sure. What if we only had 100 grams of ice in it and we came up with 136? Probably not going to happen. Okay, but again, these are the types of questions where it's really just Q equals mc delta T and then applying that answer to something else. But these are the types of questions that start to get a little bit trickier. Okay, example 3, another one. Okay, a student conducts an experiment to determine the solubility of AgCl, silver chloride, in 2.5 molar sodium chloride at various temperatures. So we can see different temperatures down here. We can see the mass of silver chloride dissolved. So it's the grams that dissolve for every 1,000 grams of solution. Some silver chloride remains in the container at all temperatures studied. The data are plotted on the graph below. So a 1,000-gram sample of a saturated solution at 100 degrees is cooled to 60 degrees. So it was at 100 degrees, and now it's cooled all the way down to 60. So how much of it was dissolved at 100 is 0.9. And how much is dissolved at 60? I would say each of those lines represents 0.02, right? 0.32, 0.34, 0.36, 0.38, and then 0.4. So this spot right here, I would say represents 0.32. Okay, so how much would precipitate out of the solution at that time? Well, you'd go from 0.90 dissolved in the 1,000 grams down to 0.32. So you subtract those two. 0.90 minus 0.32 equals 0.58 grams would be the correct response there. And then part B, the specific heat capacity of the solution is 3.4. How much heat is released? So that's Q. Q is equal to when 1,000 grams of the solution is cooled from 100 to 60. Now, here's where you got to be careful, okay? Because it says 1,000 grams of the solution, okay? The specific heat capacity of the solution is cooled from 100 to 60. You've got to make sure that everything coincides with each other when that happens. Okay, so the question is, which mass do we use? Do we use the mass here, the 0.58 grams of the amount that precipitated out, or do we use the 1,000 grams of the solution? It depends on what the specific heat they give you. They don't give you the specific heat of AgCl. They give you the specific heat of the solution. Okay, so therefore we have to use the mass of the solution. So we've got 1,000 grams times 3.4 joules over grams degrees Celsius, and then 100 to 60 is a 40 degree drop. So we're going to go 1,000 times 3.4 times 40. Okay, equals Q equals 136,000 joules, or again 136 kilojoules would be a correct response as well. Either one would be fine.